look at another example. In this example, we are interested in proving that the limit of x cubed minus 4 over x squared plus 1 is equal to 4 over 5 as x is approaching 2. Alright, so we want to show, so for our scrap work, we want to show that for any epsilon which is greater than 0, there exists delta which is positive, which of course depends on epsilon, such that if the distance between x and 2 is in between 0 and delta, then the distance between x cubed minus 4, this rational function, and 4 over 5 will be less than epsilon. Okay, so first we observe that the distance between x cubed and 4 and x squared, the distance between this rational function and 4 over 5 using some algebra is really nothing but this here. Okay, so this is just pure algebra. Okay, so that will be 5x cubed minus 20 minus 4x squared minus 4 over 5 x squared plus 1. Okay, so that this will be, okay, we simplify things, so we should get 5x cubed minus 4x squared minus 24, okay, over 5x squared plus 1, and we can remove the absolute value from the denominator because it's positive. Okay, and now I will use long division to and I'm not going to go through the steps of the long division, but you guys should pause the videos. You all should pause the video and verify for yourself that indeed the numerator factors as follows. It becomes 5x squared plus 6x plus 12 times x minus 2 over 5 times x squared plus 1. Okay, now, okay, so we need we'll need to do some work here to really, so I can control this thing here, right? So I would like to be able to control all of this down here. Okay, so there's some work that needs to be done. So first, note that if the distance between x and 2 is less than 1, this is equivalent to the fact that -1 is less than this thing here, which is equivalent to 1 is less than x, which is less than 3. Okay, by adding 2 everywhere, and this gives us the following. So if I multiply this, first of all, if I square this, then we get 1 is less than x squared, which is less than 9, and then we multiply by 5, so we get 5 is less than 5x squared, which is less than 45. Okay, and then if I multiply this by 6x, I also get 6 is less than 6x, which is less than 18. And adding these two together gives us that 11 is less than 5x squared plus 6x, which is less than 63. Okay. All right. Now, so then I can add 12 everywhere, so we get 23 is less than 5x squared plus 6x plus 12, which is less than 75. And I will call this here double star. I will call this quantity here, I will call this here star. All right, now the fact that 1 is less than x, which is less than 3, implies that 1 is less than x squared, which is less than 9, and let's see, adding 1 gives us 2 is less than x squared plus 1, which is less than 10, right? And now taking the reciprocal of this essentially gives us 1 over x squared plus 1 is less than 1/2. All right, okay, so I'll call this one here double star prime. And now using star, double star, and double star prime yield, that's the fact that x minus 2 is less than 1. This fact implies that the absolute value of 5x squared plus 6x plus 19 over 5 times x squared plus 1, that's less than 75 over let me see, that'll be 75 over 10. Yeah, okay, so I need to multiply, sorry, I need to multiply this here by 5, right? So we get 10 here. Okay, very good. So this is less than 75 over 10. And then divided by, simplifying, we get 15 over 2. Okay. So then star becomes less than 15 over 2 times absolute value of x minus 2. And so to make 5x squared plus 6x plus 12 over 5 times x squared plus 1 less than so which is less than 15 over 2 times absolute value of x minus 2, to make this less than epsilon, it suffices to make sure that the distance between x and 2 is no more than 2 epsilon over 15. Why? Because if you were to solve this inequality here, for the absolute value of x minus 2, you get that the absolute value of x minus 2 is less than 2 epsilon over 15. Okay. All right. So we have we need there are essentially two restrictions to make, right? You have this restriction, and then we have this restriction. And as long as we have those two restrictions in place, then we can make the distance between the rational function and 4 over 5 less than epsilon. So our delta here, for everything to work, we'll choose our delta to be the minimum of 1, yeah, and 2 epsilon over 15. All right, so that being said, then we can then write our formal proof. So proof. Given epsilon be a positive number, I will let delta, which is a function of epsilon, be the minimum of 1 and 2 epsilon over 15. Then this distance, which we've worked on previously, is we've seen that would be 5x cubed minus 4x squared minus 24, absolute value of this, over 5 times x squared plus 1, and that's x minus 2, absolute value of x minus 2 times 5x squared plus 6x plus 12, absolute value of this, over 5x squared plus 1. And okay, so we call this here star, and assuming that this condition holds, since x minus 2 must be less than 1, I will now recreate all of the previous computations earlier. So I'll recommend that so on the homework that you do when you're writing your formal proof, but for the sake of time here, I will just assume that these computations have been done and written, and we get this estimation here. This will be less than the absolute value of x minus 2 times 15 over 2. So you should definitely put more details here in your scrap work. I mean in your formal proof. And since 0 is less than the distance between x and 2, which is less than 2 epsilon over 15, then we obtain that star, which is less than the absolute value of x minus 2 and 15 over 2, is less than 15 over 2 times 2 epsilon over 15, and of course this will cancel each other out. I'm sorry, this will cancel each other out, and we just get epsilon. So therefore the limit of x cubed minus 4 over x squared minus 4 plus 1 as x is approaching 2 is equal to 4/5. All right. Next, let's introduce the concept of the sequential criterion. The sequential criterion for limits. And our first theorem says the following. The sequential criterion for limits says the following. If you let f be a function between two sets, A and R, where A is a subset of the real numbers, and let C be a cluster point of A, then the limit as x is approaching C of f of x is going to be equal to L if and only if for every sequence xn, for every sequence xn in A that converges to C such that xn is not C for every natural number n, we have that the limit as of fxn as n is approaching infinity will be equal to L. So the sequential criterion says the following. If the limits of f of x as x is approaching C is equal to L, then if you take any sequence which is going to C, then the image of that sequence will go to L. And I will leave the proof of this theorem as an exercise, and we will move to the divergence criteria. So the divergence criteria says the following. Let A be a subset of the reals, and let F be a map between A and R, and let C be a real number. Let C be a real number such that C is a cluster point of A. First, F does not have a limit at C if and only if there exists a sequence xn of natural numbers in A with xn not C for all natural numbers A, for all natural number n, I mean, such that f of xn, when n is a natural number, does not converge to L. Okay, and then B, we say that f does not have a limit at C if and only if there exists a sequence xn of natural numbers in A with xn not C for all natural numbers, such that converges to C, but f of xn does not converge in R. I feel like I forgot something here. So here there exists a sequence with extend. So there must be here such that xn converges, such that xn converges to C. All right. Okay, so let me stop here and then try to explain this divergence criteria. So the divergence criteria hinges upon the sequential criteria, right? The sequential criteria tells us that if you have a map between A and R, a function defined on a set A, a set of real number A, and if C is a cluster point for A, then the limit of f of x when x is approaching C is equal to L if and only for every sequence which is going to C, the image of that sequence will go to L. And of course, so we are now looking at the negation of the latter statements, and the negation of the latter statements is that if you can find a sequence which somehow is convergent to C, but somehow its images does not converge to L, or it does not converge, period, then that would be the negation of the second statement inside the sequential criteria, which then will be equivalent to the fact that f does not have a limit at C. Okay, all right. So let's look at an example here. Right. So if we let f of x be equal to 2 over x, for example, and we let xn be a sequence. So let this be a sequence given by xn is equal to 1 over n. Then I believe you agree that the limit as n is approaching infinity of 1 over n is indeed 0. However, the f of xn, right, will be 2 over xn, which is 2 over 1 over n, which is 2 times n. And clearly you will agree that the sequence f of xn which is the sequence 2n, as n is going from 1 to infinity, is properly divergent. In the sense that its limits, the limits of 2n as n is approaching infinity is infinity. So then we can then say that the limit of 2 over x as x is approaching 0, right, does not exist. Because we have just found a sequence which is going to 0. This is y is equal to 2x. Right, so we found a sequence of numbers going to 0. We have a sequence of numbers going to 0 somehow. And if we look at the image of that, you can see that it's blowing up, right? It's going to infinity. So clearly there is no limit at 0 for this function. Okay, so let's look at another example. Let f of x be the function 1 if x is positive, 0 if x is 0, and negative 2 if x is less than 0. And now I will let xn be the sequence, given by xn is negative 1 power n over n. Then you will agree from our previous work this semester that the limit of xn is indeed 0, right? So this is an illustration of what's going on. So this is 1, and open here, and then negative 2, in there. This is the graph of this is y is equal to f of x. Okay, now first note that the limit of f of x2k as so if we look at this, the subsequence x2k, then that will be the limit as k is approaching infinity of f of 1 over 2k and because that's positive, because k is a positive number, then 1 over 2k is positive, then it will be somewhere here, right? So 1 over 2k will be somewhere here, so then this will be 1, right? It's always 1. So the image of the subsequence x2k is going to always be 1, and on the other hand, the limits of x2k plus 1 will be, because x2k plus 1 is odd, that would be negative, it would be f of negative 1 over 2k plus 1, right? If you plug that into this sequence here, if you plug it into this sequence here, and then because negative 1 over 2k is negative, so we have negative 1 over 2k plus 1 somewhere here, that will be negative 2. So we observe, this is what we observe. We observe two phenomena. The limit of f of 1 over 2k when k is approaching infinity is 1, and the limit of f of negative 1 over 2k plus 1 as k is approaching infinity is negative 2. So thus the sequence f of xn, right, we have found inside the sequence f of xn two subsequences converging to different limits. Therefore this is not convergent and we conclude, therefore we conclude that the limit of f of xn, I'm sorry, the limit of f of x, not f of xn, the limit of f of x as x is approaching 0, we have found a sequence which goes to 0 but its image does not converge, does not exist. Alright, and this brought us to the end of our video. Alright, so there's a lot going on in this section. This is a very important section for us. It's a very important concept for us. So it is imperative that you really try to digest all of these ideas, that you own them, that you know them, that you remember them, that you understand these concepts. Because as we are moving forward, everything will build upon these principles. Thank you for showing up for our introduction to the concept of limits, and I hope that you'll show up for the next video. Thank you.